Hi, Hitar. Can you hear me? Hitar?
Yeah, I can.
Yeah, let's wait for some more time. So there is until a
Yeah,
few more people join. Yeah.
yeah. Let's wait for 5 minutes, I guess.
Yeah, 5 minutes. Yeah, we have one. Hello? Did someone say something?
I think someone's microphone was on by mistake. So.
I have made you a co-host, so you should be able to.
Hi. So, is my screen visible to everyone? Um, Hello. Am I audible?
Yeah.
Yes, you are audible. You can go ahead. Start.
Okay. So, I think we can start now because I think everybody is here. Okay. So, in this lecture, we'll be discussing about these learning algorithms, and it's just introduction. So we will look into backpropagation in detail in the next lecture. There will be some detail in this lecture, and it will be completed in the next one. So yeah, wait, just give me one. Yeah, so before starting, I'll just mention that what is our plan. So today we will just get some basic intuition for backpropagation. Tomorrow, sorry, the next lecture, we will discuss it in detail and also see the implementation in Python and maybe in MATLAB if possible. And after that, next week, we will have a tutorial in which we will build some neural network and using TensorFlow or maybe by from scratch, maybe without using any library. So that will be decided later. So this is the plan for the next 3 lectures at the very least. Okay. So I think we should start. All right. So for just a recap, last time we saw what a perceptron is, what are activation functions, and we learned about the structure of neural network and what is, like, briefly we discussed learning, and we saw a few examples. So so I'll start with the last example that we were discussing. I was hoping to finish it, but I don't think it will be possible. So we'll take it forward in the next lecture. But this is what we had at last time. So we had this neural network in which we had 16 inputs, and there were 6 hidden neuron and 3 output neuron, and we wanted to identify these shapes. So let's call it L, cap, and square. So the task was that what weights, and of course, whenever I say, let's say what weights, just understand what weights and biases. So what weights and biases should we select for this neural network so that it can identify these things. So this we will do maybe in next lecture, but okay, let's go ahead. So what is learning? So last time I think I described that learning is basically reducing the error of cost function. So, but for the overview, so there are three kind of learning, but we are only just looking into learning for now. And of course, we will only be discussing this one in detail. So supervised learning is what I described last time. So you have input-output pairs, a set of input-output pairs, and you need to learn a function that can map the input to the correct output. And its example would be regression or a neural network. Yeah, this is, so in supervised learning, you are given a data where you want to learn a function. In unsupervised learning, and of course, there's input output. That's very important. In unsupervised learning, you are given unlabeled data and you need to find some pattern in it. So for example, it might be that you are given few points, let's say, just you're given few point, and there's some, you have to infer that, okay, these form one cluster and they form another cluster and so on. So this is what unsupervised learning would mean. Okay, but I don't think there are good ways to do it using neural network. I mean, at least I have not studied them. So we don't even need that. So we will just discuss supervised learning. Okay. So a neural network is a function. I think that was pretty much clear from the last time. So it's when you do all those multiplication of weights, applying the activation function. So at the end of this lecture, we will see this function a bit more closely, but it's a function. And for each training example that you have some associated cost, and cost is or loss, which is basically, which tells you how much you are missing your target expected value. So you are getting something and you wanted something else. So the difference, you square it or do something. So cost function, last time we just saw one of the function, which is least squares or mean square function. But there could be multiple, like binary cross entropy, or you can use like L1 norm or different kind of norms. So norms are also a measure of, so you just want to find out, you associate a value with whatever the difference you are getting from the expected value and your actual output. So, but it's good to have a good cost, normal cost function, and for our purposes, L2 will suffice. So we are just, we'll just be using L2. So when we see learning, so it refers to the process of finding the weights and biases that minimize the average cost for all the training examples. I'm sorry, I missed to write this is not per. So this is average cost over all training examples. And that minimizing that average cost is what you call as learning. Okay. And now, because learning is kind of a minimization problem, so you can see all of this field as an optimization, everything falling under optimization. So you just want to, given a function, you want to find out some parameters that will minimize that function. Or let's say you will be close to the minimum. So when we will discuss underfitting and overfitting, we'll understand we don't actually want uh, the minimum, the actual minimum. We just want to be close to the minimum so that we can preserve the structure. We are identifying the structure and not actually just memorizing all the data points. So this will become clear maybe in the next lecture. Okay, so this is quite basic. I think, I mean, of course, I mean, we all know that, but just let's revise this for in quickly. So in case of 2D function, we know that to find the minimum of there's a minimum. We just writing this, so there's a minimum. We can be sure that there is a minimum, and we want to find out the minimum. So we just set the derivatives to 0, and we solve for x, and that should be the minimum if it's a convex function. So this is it. So this is the tangent. So it's pretty like basic to understand why it is the case. So if I'm here, so derivative is negative, it means that if I move ahead, the function will further decrease. So it means that at any point where the derivative is not is negative, let's say, then the function will further decrease if I move in the positive x direction. If the derivative is positive at a point, then it means that the function will decrease if I move in the negative x direction. So it means that these points can never be minimum. So only this point is a last hope, that where the derivative is 0. Of course, it could be saddle point or something, but let's not worry about it. Let's keep things simple. Now, if we go to multi-dimensional case, so we want to find a minimum of a multi-dimensional case, or let's say it's very important to understand, or approach the minimum. We don't actually want to find the minimum. We want to approach the minimum, and we'll stop before actually getting the minimum. So it's exactly as I said, it's because we don't want to memorize the data point. We want to generalize it. We want to find a structure. So for that, we use something called as gradient. So again, most of you will be familiar with this, but let's just revise and go through all of it. So what is gradient? So I have a function f, and I define the gradient as this column vector, del f by del x1, del f by del x2, till del f by del xn. This is partial derivative of f with respect to x1, with respect to x2, with respect to xn. And that is what is nabla f. So so what is partial derivative? Just for the sake of completeness, you differentiate f, treating all the other variables as constant and only treating this as an actual variable. So that's what partial derivative is. So geometrically, what it means is that you have some function. So let's just try to see. Yeah. Wait a minute. Yeah. So you have some function, and if you are at some point here and you move in this direction, let's say in the x direction, and you are not changing your y value. So whatever function is there, you are not changing the y, you are staying at y, and you're just moving in the x direction. So whatever the rate of change you will get for this slice, so it's basically intersection with the plane, and that is what del f by del x will be at this point. Similarly, if you move in this direction, then that would be del f by del y. So this is x, this is y, and this is z. So that's what we like. For now, this is enough. Okay. Now look at this formula here. So you have a function x for fx1, x2. It's dependent upon two variables, and you are at a point x1, x2, and you move slightly in the direction delta x1, delta x2. So this is a vector which is telling you how much you move. So the new position will be x1 plus delta x1, x2 plus delta x2. And the change in f will be given by delta f equal to del f by del x1 dot delta x1 plus del f by del x2 dot delta x2. So it's basically saying that if you want to find out the net change in f, so of course it's an approximation if you actually put the values, but in the limiting case, we can assume that this is true. So this is telling us that if you are changing x1 and x2 by this much amount, and you want to find out how much f would change, so you can first of all calculate this thing. So without caring about the change in x2, you are calculating how much f would change if due to the change in x1. Then you calculate how much f will change due to the changes in x2, and then you add those changes to get the net change in f. Okay. So this can be successfully written using this equation. So delta f is equal to nabla f. I take a transpose. I evaluate this gradient as x1, x2, and I dot it with delta x1, delta x2. So there's an important reason why we are seeing it as vectors. So remember, this is the evaluation of the gradient at a particular point, and you are taking the dot product with this delta x1, delta x2. So let's call this motion vector or something of this sort. So we are moving in this along this vector from the point x1, x2. Uh, now, so there are two steps to find the total change in f. You first of all find the gradient at the given point, and then we do some sort of multiplication of two vectors. So it's important to understand multiplication of two vectors. So this is a dot product. So this is from Wikipedia for the source. So you have a vector b and your vector a, and if you take the dot product, so it's basically like projecting this vector down to this and then multiplying their lengths, right? So if this vector is, let's say, perpendicular to it, this a vector is perpendicular, then the dot product would be 0 because there is no projection. So for a given length of this vector a, so if I fix this length that I don't want to move too much, and I'm saying that how much, okay, so I can move perpendicular to this vector or I can move parallel to this. So to maximize this dot product, this vector should be parallel to it. So if v1 and v2 are two vectors and if we want v1 dot v2 should be maximum, then if the only parameter that we can change is angle, then we should make them parallel to each other. So if we make them parallel, then the dot product would be maximum for that. So of course, this part nabla f, that is the gradient, this is not in our hand. So this depends on function and the starting point. Because we are only choosing how much we should move, so we can choose this vector. So delta x1, delta x2, this is something which we have a control over. And that's why we should choose this delta x1, delta x2 such that it is parallel to this vector. Note that this is not a function, because once you calculate this nabla and then you evaluate it at a particular point, you get a value. So it's a vector, let's say 0.2, 0.3. So you move along that direction. And if you move along the direction, you will get the maximum change in delta f for, let's say, given length of this vector. So here's a very simple question. So this will give you maximum positive change, right? Because that's how we did it. We're just finding what is the how to maximize the positive change. So for maximum decrement in f, so if I want to decrease f as much as possible, because that's what our goal is, to minimize f, what should we do? So we should ... Please, if somebody would like to speak and just answer, it's very trivial, of course.
We should move directly opposite to the gradient, right?
Exactly. So we should move in the direction opposite to nabla f, that is gradient, and at that particular point, and that is what gradient descent is. That's the main point of descent. So it's just that you calculate the gradient and then you move in the opposite direction to nabla f, and you will do it iteratively. So we'll see this in detail just after this. Okay. So gradient descent. So I wanted to like explain this using matrix, but I don't know if I actually did that or not. So let's just see this. So to minimize the function f, we need to move the direction opposite to nabla f. So this is nabla f. I mean, I again missed to fix this. So this is nabla f. And so what I will do is, suppose I'm at a point x, and the gradient at that point is nabla f. So I update my point. I set it x prime equal to x minus s dot nabla f. So what is this s? So this s is just the step size. In the context of deep neural networks, we call that as learning rate. So I mean, maybe if you remember the example that I gave you last time. So we had to very carefully choose. Okay, I cannot even. Just give me 1 minute. Okay. Yeah. So if you have some function and you are, let's say, trying to minimize it, and you are here, then as you move in this direction, if you move too much, then you might overshoot. If you move too little, then it will take so like a large number of steps, and that might be really bad. So choosing the step size is not a very easy task. And in the libraries like TensorFlow, they have functions which do not require you to explicitly mention this thing, this s, and they will just identify that and change it dynamically. So TensorFlow provides that, but I don't actually know how they exactly do that. But we, for our purposes, even if we choose some fixed value like 0.001, 0.002, or some okayish number, then it will work. It should not be too large, be okay, or just a normal size epsilon. Okay, so just to understand this, that this will definitely decrease your f, that is the cost function in the case of DNN. Just notice this equation. So we go back to this equation here. So delta f is equal to nabla f dot this change. Okay, so this change is basically, so if I'm reaching at a point x prime, and I was at a point x, so this change is x prime minus x. Now come back here. So what is x prime minus x here? So it is basically negative s times nabla f. So this is what your delta x is. Now, what is delta f? It would be nabla f dot product. You take the transpose also just for the dimensionality, and the minus s times nabla f. But s is a constant, so it goes out, and you get simply minus s times nabla f norm whole squared. The point is that this is a positive quantity. So this, because s is also a positive number, this whole thing becomes negative, which basically means that when I move in this direction, my function will definitely decrease as long as this is non-zero. It's much like the 2D case where whenever the derivative is not, until we reach this point, we keep on decreasing the function. So as long as the derivative is not zero, we will somehow approach minimum. Same case here. So that is what gradient descent is. At least mathematically, we have the implementation, and the heuristics are, of course, this gives rise to the whole field of this deep learning. But this is the basic idea and the mathematics of gradient descent. So yeah, if there's any question till now, then you can ask. I'll wait for 20 seconds. Okay, cool.
Okay, go ahead.
So, I mean, okay.
Yeah. So Hitarth, I just wanted to clarify one thing.
Yeah, go ahead, Madhukar.
Yeah. So in the last slide, can you
This
move
one,
to the
right? Okay. Which
the
one?
last? Yeah. Yeah, the one before that. Yeah.
This one?
Yeah. So when you say that the change in f is given by this, is this the change in f, or is this the direction in which the f changes?
No, this is the change in X. So when you multiply these two quantities and you sum it up, so you get a number, let's say a real number. So this is the actual change in F. By what amount? It is not a vector. So it's a number because you are multiplying two vectors. This is, let's say, a row vector and this is a column vector. When you multiply it, you get 1 by 1 matrix, which is a number.
Okay. So the step, so the size of the step is somewhere hidden in this, right? The step size, which you explicate later, is somewhere hidden in this, right? Because how much you move has to be a part of the change.
Yeah, so step size is actually inside this, exactly. So that's why I even described it here that delta x is equal to negative s dot nabla f. So yeah.
Yeah.
Okay.
Yeah, sure. Thanks.
Okay. So before doing this, actually I wanted to go to this some website that I wanted to show you. I don't know how many people of you are familiar. Uh, let's go through it. So um, first of all, I ask you, maybe we'll do it in
Yeah.
so do you guys, have you guys seen this site playground.tensorflow.org?
Yeah. Before you move to
Yeah.
the one question, so this method, the guarantee that you will be moving towards minimum in the way that you explained by gradient descent works only for certain kinds of functions, right? You have some weird functions, spiraling or different things. There's no guarantee that this will find the minimum. This is
Yeah,
all.
if a function is really messed up and some if it's like varying too much than your step size, then maybe you will never find the minimum using this. So it is possible, of course.
So that's why for all, you did not define convexity, but this is supposed to work for all convex functions. For convex functions, assuming that we give a definition, so is that supposed to work for all convex functions? Is it guaranteed to work for all convex functions or no? I mean, that is, I mean, you in the beginning you said convex functions, but that required, I mean, is that guaranteed to work to find the minimum or close to it for such functions, for convex, as long as they are convex?
So I think yes, it will work for, at least for the cost function that we use. All of them are ultimately the whole result is convex. So
okay,
I think it does work at least for the function that we are interested in, and this method will definitely work for all functions, all convex functions, as far as I know. But defining convexity, it will require some, like, it will take a long time, and it will be a bit hectic, and you have to do this Hessian and all. And I mean, I'm not even prepared the slides, and it will take a long time. So I just left that out for the better. So I think we can move
I have
on.
a slight question on this. So,
Yeah.
so this the minima that this will approach the minimum. It's not a global minimum, right? It's some sort of a local minimum.
Of course, yeah, exactly. So that's why sometimes if we are not getting the accuracy that we wanted, we reinitialize everything and we again start, so that if this point is not working, maybe this point will work. So of course, it's not a global minimum, but there's something. I mean, I've not gone into the mathematics of that, but in there's some paper. Maybe I will share the link on Moodle, which says that in high dimensional something happens that you can, the local minimum that you find it mostly very good, like it's from any point you will actually reach your global minimum, or very close to global minimum at least. So I'm not sure why that works and what geometry is there so that it happens, and maybe people even have not defined that properly, but they say that there's some structure in high dimensional shapes that we are dealing with, that the local minimum that you are finding from random point, starting from random point, it usually very close to your global minimum.
I see. That would be a really interesting thing.
The function is convex globally, right? So
I,
there's no.
I won't say you need globally convex. So I mean, at least around that point, that is what we wanted for this part. If it's convex globally, then I think I'm not. Maybe there's one minimum, right?
Yeah, then there is a unique minimum.
Hitarth, I think you're going to
I'm not
discuss.
saying it's globally.
Hitarth?
Yeah.
Yeah, I think you're going to discuss SGD later, right? Or no?
Yeah, I wanted to discuss. I think if there's time, then I will definitely do that.
Yeah, I think that'll probably clear out some doubts about global versus local.
Yeah. Right. Okay. So let's go with the back. So I wanted to ask you guys that how many of you have seen this playground or TensorFlow.org? So anyone has seen that yet? If nobody speaks up, then I'll assume that nobody has actually played with it. All right, so we will come to this at the end. It's a bit cool to understand, and you can play with it before going to, before implementing your neural network. So which you will after next lecture. So first, today we'll just look at the intuition for this back application, and we will in the next lecture we will understand how exactly it is done. So for now,
Hitarth, I just want to add for people, because more you said most people have not seen it. Yeah, so wait till the end. So that's a cool demo that he has.
Yeah, so it's yeah, we will.
I found it cool. So let's go.
Yeah. Okay. So for now, what we need to keep in gradient descent is basically updating your. So what is this X? If I ask you that, what do you think this X would be in case of a neural network? Would it be the inputs or something else? Just it's a very simple question. If somebody would like to answer it.
It will be weights.
And biases, of course, true. So this X would be of some sort W and B. So X would be. It's important to realize that, okay, we are not updating the input. We cannot change the input examples, right? There's no sense in that. I mean, as far as I don't know if there's any sense in that, but we want to change the W and B, and that is what X would be. So, okay. Now, before going to the backpropagation in in the intuition, let's first of all see what we are trying to do. So, okay. So suppose I have, I better use this example. Okay, so just see this picture. So I have some input here, some neurons are here, and something is coming out. And let's say these weights are initialized randomly. So you can see the weights here, or minus 40, minus 1.8, whatever. And 0.40, of course, and so on. So when I pass a point to it, it will just flow through it, and some calculation will happen. And then you will activate this or this, or maybe both with some value, and the net result would be displayed here. So that is what is going on in this network. So suppose if I'm off by some value, if my output is not what I wanted, then as we saw, we have a cost function which will quantify that, how much, by what amount I'm off from my expected output or expected output. And then I will like to change these weights, and then these weights, and then these weights, so that our loss is minimized. And we take average over all the training examples. As I said, so when I say all the training examples, suppose I have 1 million examples. So do you think we should actually take the minimum over, we should calculate the gradient for all the 1 million examples and then proceed? So practically, it's not a viable thing to do. So what we do is we create what is called as mini batches. So that is what they are showing here, batch size 10. So it's showing that what is the size of one batch. And then you randomly select 10 training example, and you evaluate the cost function over those 10 examples. So instead of doing it, let's say in the whole training set, I have 10,000 examples. So for each update, I'm not going to calculate the cost function for 10,000 examples, which will take a long time. I will do it for 10, and then we will move back and we will update these weights and so on. So that what this stochastic gradient descent, the idea of this thing is that you randomly select few 10 or whatever batch size number of training sample, and then you perform the same thing just as it was your training training data. And then you do it again, and you do it until you exhaust your full data set. And I think that is what they call as epoch. I mean, yeah, that is what they call as epoch. And then you repeat this process.
What is the input to the neural network here?
So input are just two coordinate, x1, x2. So they're just xy coordinate, let's say for now. So I will explain this all in detail. So what is going on here? I'm just using this picture because this is really clean. So I'm just trying to use this to explain you what this backpropagation wants to do. So you have some output here and you want to decrease or increase these weights. So let's say the function is C. So you calculate, this is...
I think the question was given was, what exactly is this neural network trying to do?
Actually, see, it's trying to cluster, right?
Yeah, it is supposed to cluster.
Unsupervised thing, right? And we neural networks are supervised.
No, this is not unsupervised because they have the output that, okay, these points are orange and these points are blue. And the task of the neural network is just to identify a boundary which will separate them. So it's not unsupervised. Is it supervised?
Okay.
So we will discuss this in a bit more detail later, but for now, I just want to use this picture. That's what I'm saying. Let's not go into all these crazy things here. Just look at, just think about this. So you have some cost and you want to find the derivative, the partial derivative with respect to this weight. And then you update your point and subtract that by the, let's say S is your learning rate. Here it's 0.03. And you subtract that with your weight. You calculate the gradient. So you are exactly doing this thing, right? But to calculate this gradient, you need to do it for all the parameters that you have. So if you have 100 and 1000 weights and biases, then you do it for all the 1000 weights and biases. You calculate this gradient, and then you multiply that by some learning rate S or step size, and then you update all the weights and biases. So that is all we want to do. So the whole idea is, how do you calculate these gradients? So what is the problem with the normal, you'll say just differentiate with respect to, let's say this is W1, W11, W12, and so on. And then you just differentiate with respect to something and do, I mean, we'll see why it's so hard to do and why backpropagation makes it very easy. So that's what the goal of this part would be. So this is from some lecture that I saw, I don't know, a while ago, and I will try to like explain. I have my notes, and I will try to explain that this intuition using that technique. Instead of going directly to backpropagation, we will start from here. So, what is a computation graph? So, it is basically, let's say, it's very simple thing. So, if I give you an expression like 2 plus 3 into 5 and something plus 100 and so on, how the computers actually calculate it? So they start from the innermost part, they calculate something for this, they sum of this, then you multiply this, and then you add 100. So it's like that. You first of all you have 2 and you have 3 and you take the sum of them, you get some number, and then you multiply it with another number. So you have another number here, and you multiply it, and that's how you will get the next value, and so on, right? So this is what the computation graph is for this expression. Just give me 1 second. I think just give me, let me pause this share for just a while. Sorry. I think this issue. sorry, yeah. So that's what a computation graph is. Okay, now let's see the same thing for a function. So suppose I have a function which is fxy, and I define that to be x squared times something like, let's say 3x minus 4y plus y squared. Okay, so we want to find the computation graph for this. Unfortunate that okay. Yeah, so how do we do that? We start from these blocks and we say this is x and this is y, and we calculate the first thing. So we can go like in the order of precedence. So you calculate this thing. So this is your x squared. So I don't know what the hell happened with Zoom. I think Zoom changes this bad somehow. Okay, I hope it's okay to write a bit nasty, but we have to do
I
this
think
because
it was
there's no
fine.
option.
Yeah.
Yeah, I think there's something with Zoom that it, I don't know, maybe something is wrong with Zoom. So it just stops working when I use Zoom. Otherwise, it works very well. Okay, so here it is 3x minus 4y. So you see that this part actually doesn't depends on the previous calculation. So similarly, I will also calculate y squared. So it's also in parallel. And then we multiply both of them and we get, what do we get? Okay. Maybe I'll have to use my previous writings for this. We get the multiplication of this. So let's name this L0, L1, L2. And here you get, okay, let me remove this. Yeah, so you will simply get L0 times L1. And from here, you will add that. Let's name this L3. And your output would be L2 plus L3. Okay, so this is your computation graph for this, at least the, not the computation, we are not computing yet. So now we will fix some values. So we will set, let's say x is equal to 1 and y is equal to 2 or something of the sort. And then we will flow through, we will just pass those values in this graph. So when you pass this from here, this will become 1, right? So let me change the color. So this becomes 1. When you come here, is 3 minus 4, 2s are 8. I mean, 3 minus 8 minus 5, and so on. So you can, we can evaluate this. This is 4, and then these are multiplied L0 and this, and this will give you minus 5, and then you add them up, and it will give you minus 1. So this is just a simple thing. Okay, there's one resemblance here. So every time I go from this, let's call them node, to another node, this is directed graph. First of all, you can calculate that value using the previous values, and at each step, it's a pretty simple operation. So here it's a very simple operation, 3x minus 4y. Similarly, this is a simple operation, y squared, and then you just add this and you multiply it here. So this is something called as topological sort, and you can do that to find out which thing to do first. And then we calculate the function. Of course, it might seem a bit weird why are we even doing this. So maybe I will have to, okay, I even lost that. All right, so let's see what is the derivative of f with respect to x. So suppose I want to find out del f by del x, okay? So what should be the way? If you start with this function, you would simply differentiate these parts, right? So if I want to find out del f by del x, I will first differentiate this, and then this, and then this, and then I'll apply proper rules for that. So if there's a multiplication, then I'll apply the product rule. If the addition, then the sum of different partial derivatives is partial derivative sum is sum of partial derivative, and so on, like simple rules, and I'll get the derivative, right? So for finding del f by del x, I have to pass through the whole graph, and for each node, I will have to compute the derivative with respect to x, the partial derivative with respect to X, and then I will combine them somehow and to ultimately reach here. And this is my output. And that will give me del F by del X, right? So I hope there is no doubt about this, right? It's very simple thing. So this is what you call as, so let me go back. So this is what you call as forward mode differentiation. So you are just moving this way and you are calculating derivative. So what is bad in this approach? So it is, suppose I have a 1000 parameters here. So what will happen? I will have to pass to the whole graph 1000 times. So for each parameter, I will have to do the same process, differentiating node and this node and so on to ultimately reach the final node and get the derivative. And that is what is bad in this with this forward mode differentiation. And the idea is to use something what they call as reverse mode differentiation, or it's also called as, okay, let me just remove these points. Yeah, it's also called as automatic differentiation and so on. So let's try to go do that.
So Hitat, what you're saying is in this forward thing, of course, you have to propagate the difference. We have to to compute the differentiation for each sub expression. I mean, you have to propagate through the. No, it's not quite clear to me. So, you have to see delta f delta x for the entire function is computed in terms of the sub expressions, the deltas for each of the sub expressions. Now, so what is, I mean, so you don't need to propagate the entire graph, do you? I mean, the entire computation graph, do you have to propagate? Why? That's not clear to me.
So suppose there are, let's say, every node can have input from other variable, right? So this y is going to these two things, right? It might also be the case that it's also going to this node and so on. So in the worst case scenario, you have to travel a lot. You have to travel a lot. You start from here and you will just find all the terms which contains y, and you differentiate with respect to y. And then you do this for this node, and then you start to apply the product rule here, then sum rule, and then you will finally get your output of this df by dy or df by dx. So you have to do the whole process for each parameter separately. That's what I mean by this. So what is not clear here? Sorry, I think it was lost. So yeah. So I mean, I'm not getting what is not clear here. Can you repeat, please?
I mean, what I'm saying is you don't have to go through that entire network each time. So I'm saying for sub-expressions, you'll only need to go for part of this computation graph, is what I'm saying.
Yeah, so maybe not the whole, but in the worst case scenario, it will be like, it might happen that it goes through a lot of nodes, let's say half the number of nodes, but still if you have 1 million parameter, then it will become really, really slow. That is all that we should take away from this, that this is not cool, at least because we just have one output and we have to do this. We'll see, I mean, in the next part, when we do the reverse, I think it will become clear why the other thing is better, okay? All right, so we don't have that much time, so let's go over this quickly. So in the reverse, what we do is we start from here and we will write this thing. So first of all, we'll calculate all these values. So these red things are values. I'm sorry, this writing is really bad. I had this this ready actually, so I'm trying to, that was I'm trying to find out that I wrote all this a while ago. So it's something which I cannot find out now. Okay, I think it's not possible. So let's just go. Okay, so these red values are telling you the actual value of these nodes, and we will keep them. And in the blue, I'll be writing the backward reverse direction for this. Okay, So we start from here and we just write, okay, so what is df by df? So it's definitely 1. So we don't care about that. Now we go back to this node and let me just drop this like this. Okay, this is L3, right? So this is what is F is L2 plus L3. So what is dF by dL3? So this is dF by dL3, and from here you can see it will be 1, right? It will be 1. I hope it is clear. Similarly, you go back from this arrow here and you reach this way, and from here, I think the same result will follow because it's a sum. You'll get dF by dL2, and it is also 1. So it is 1. All right. Now from here, it is L3. Now you go back to this part. This is L0. Now, if you apply the same thing, so here we'll find this, not df, of course, dl3 divided by dl0. Okay, let me just fix this. Yeah, dl0, and that would be, so it's a partial derivative. So because there is an L0 times L1, so you just get L1 as the output. Okay. And note that you can just write the values directly. So what is L1? L1 was -5, right? If I remember, no, sorry, not negative. Yeah, L1 is negative. Yeah.
That this is L0 times L2. So this would be L0. Is this?
This is L0 times L1. Yeah,
L1.
this is L0 times L1.
Yeah.
Yeah. So you get L1 here, but we also know the value of L1. It is -5. So we can directly write that, okay, it is also -5. This is okay. Similarly, we go back in this direction, and now actually this is nothing more than chain rule. It's just that, but a nice representation for that. We'll see why it is so useful. Now you find out here. So what term would be here? So I mean, it's just for checking that, okay, you guys are listening. What should I write here? Which derivative? So I'm asking that, can anybody just speak that what derivative should I write for this
L3
node?
by L1.
Yeah, exactly. dL3 by dL1, and it would be L0 L1, and you were taking L1, it will be L0. So of course there is nice symmetry that here you got L1 and here you get L0. And after a while you will just realize why it's happening. Now you go back in this direction. Now for when you come to this node, now there might be multiple derivative here. So let's make a big box. So first we will say this one is coming, okay, L0. So you will first find dL0 by dx. So what it would be, that it would be equal to, so it is simply x squared, I guess. Yeah, so it would be 2x, and 2x from if you put the value, you get 1 as the answer, right? So this is 1. Similarly, this one is also coming back here, and okay, there's no space left, so like write it here. Yeah, so it would be dl1 by dx, dl1 by dx, and this would be dl3. Yeah, this would be 3. And similarly, there are 2 nodes here. Let's just write quickly. So dl1 by dy, and that is -4. And you have dl2 by dy, and that is 2y, and you put y equal to 2, you get 4. So I think, yeah, both, this is -4, this is 4. Okay, now we want to calculate. So this was just a kind of a single pass from the back, the last output to the back part. And now let us see what is the derivative of f with respect to x. So just see this part. df by df. This is df by dl3. This is dl3 by dl naught. This is dl naught by dx. So even though they are not fractions, let's treat them like fractions because we just want to cancel them out. So just multiply this, this, and this, and you will get one portion of df by dx. So 1 times 1 times minus 5 times 1, right? So that would be, I guess, simply minus 5. So I'm finding df by dx. So just write this here, minus 5 plus, and you add it over all the paths that are possible. So what is the other path to reach here? So this was another path. So dl1 by dx, if you multiply this by dl, okay, dl3 by dl1, and then you reach here, and it is, okay, yeah, this one, sorry, df by dl3, and then you reach here. So you just multiply along this direction. So df by df, df by dl3, dl3 by dl1, I guess, yeah, dl1, and then dx. And okay, so we should write the value of this also. So what is the value of L naught? L naught was 1. So let's just put a 1 here. Now you multiply all these things, and this will, df will cancel df, dl3 will cancel dl3, dl naught, dl1 will cancel this dl1, and you get df by dx. So of course, these are not fractions. I'm just telling you chain rules kind of looks like that you are canceling. So just for convenience, I'm just saying that we can cancel them out. And the point is that the net result that you're gonna get is minus 1, no, it's minus, no, 1 times minus 1 times 1 times minus, no, not minus, sorry. These are the values, I'm sorry. These are, we don't take care of value, we just want derivatives. So 1 times 1 times 1 times 3. So that is 3. So you put a 3 here, right? And the net result that you get is minus 2. These are the only two parts that in which you can reach here, right? Okay, I think I might have missed some negation or something. So I don't want to get in calculation, just telling you the idea. So this, I mean, you should work it out and try to see. There might be some calculation error, but let's not worry about it. Let's get the idea correct. And now if I want to find out del f by del y, I just have to find out all the paths which start from here and lead me there. So I can go along this path and I can go along this path. So I just multiply this 1 with 1 and with 4. And if I want to move this along this path, then I multiply 1 with 1 with 1 with minus 4. So ultimately you will get both of these, and this will give you the net answer, right? So if you take the sum of this, then that will give you the total answer. So if you see here that L naught L1, so the reason it was coming out to be L1 and L naught is like it's, when you do this back thing, you will realize that it is automatically implementing your product rule. We don't have to do it manually. And the second thing is, if there were 1000 parameters here, in just this one sweep, we will get all the parameters, we will get the partial derivative with respect to all the parameters in just one sweep. So that's the basic idea of backpropagation, that instead of going forward, what we do in manually in our classes or when we are solving partial derivatives, we go this way. But we are going this way in this. We are calculating all of them simultaneously, and then we just have to find out the path which lead us from the final node to the initial node, and we multiply all the derivative along that path, and we add them up. So if there are two such things, this and this, then we add both of them to get the final del f by del x and del f by del y. And if there were 1000, then they will be done. They will all be done in one sweep. So that's the takeaway from this, that this is how you do it. So how is that related to the backpropagation in neural network? So actually, this is exactly what backpropagation in neural network is. So first of all, as you saw that first I calculated all the values, right? So for that, what we do is we do a forward pass. So these nodes, they can be nodes of neural network, and you're just applying a function, right? So it could be activation function, it could be a weighted sum or something, but they're all functions. So the same idea, the same thing, whatever we are doing here is exactly what we are going to do in backpropagation, but there will be some slight modification that we will be using matrices and okay, so that this is what I described right till now, that what reverse mode differentiation is and how it gives you all the derivative kind of at once. So it's pretty like fast, and maybe the sole reason for this advancement in deep learning is that because we do it reverse. So again, if you want to read more about it, so it's also called automatic I guess no, not algorithmic differentiation, and maybe I don't remember exactly, automatic differentiation. So these are the terms that you can search on internet to, or even reverse mode differentiation to learn more about it. So there might be some calculation mistake, but definitely this is I hope the idea is clear. So if there's any doubt for this idea, then let me know. I'll wait for 20-30 seconds here.
Well, Sahil has something. Sahil, instead of typing in the chat window, why don't you say it loud?
Yeah,
Hello?
I cannot even see the chat. Yeah, please say.
Yeah, no, I was just saying, I think it was the term you're looking for, autograd.
Okay, now I think the one, I don't know if people, confusion that I had, I know that was confusing. See, you were using, you had this fxy, okay, as an expression. So you can actually do this for computing as the df of dx for that expression, correct? Through this background. Then you can actually plug in for x and y, okay? So it is not that you, I mean, there is two things here that got me confused, because you were actually using for specific values of x and y and then plugging it somewhere, and then, but basically this gives you a method of computing df of dx by following all these paths. So you can actually use it for getting the resulting expression. And then you plug in, and if you want to plug into specific points.
So, okay, so there's a reason we don't want to do that. I mean,
Why not?
Because first of all, it will require you to save all the expressions and then you multiply them and then you plug in. But actually, when we are doing gradient descent, we just want to find a gradient at that particular point. So it's better to just keep those numbers and we manage a stack. So this can be implemented, and this is actually implemented. And you keep numbers on a stack, and whenever you see a derivative, you push that on the stack. And so it becomes easier to deal all of this if you just use numbers instead of expressions. So because it's calculated right away, and ultimately when you reach this node, you will get the first derivative. When you reach this node, you will get the second derivative with respect to, I mean, y and x, y and z, whatever you.
But then if you want to do it for different values of x and y, then you will have to.
Then you have to do it again. Yeah, we have to do it again. So yeah, you have to do it again. Yeah.
One question I had.
Okay. So this is
what you're saying is, in an actual algorithm, they actually do it for specific points and they do it again, rather than symbolically computing for the derivative for expressions.
Yeah, I mean, I think if you imagine how big the expression would be, just imagine there are 784 neuron and then there's something. I mean, it would be gigantic. So I think that's why they don't actually do it symbolically.
Okay.
Yeah. Okay. So
any other questions from people?
Yeah. So if there's any question, then please let me know.
I guess not. Yeah. Okay.
Yeah. So you should. I mean, I would suggest you that you should learn more about it and see a few examples and do it by yourself. And whatever mistake must have made in this, you should try to do it by hands to understand everything. So let's just.
The only mistake you made was you wrote 2x equals.
Yeah.
The only
Okay.
mistake you made was you wrote 2x equals 1 instead of 2x equals 2. Otherwise, I think it's perfectly fine.
Oh, yeah, I guess, yeah, true. Yes, right.
And also here you wrote delta F by delta L2. Is that correct? The bottom.
This one? Yeah, this is correct, because you are directly going to F, right?
Okay.
And this node is named L2, so you just
Correct.
take df by dl2.
Right.
Yeah, so now,
You're correct.
so, I mean, of course. All right. Now I'll just like mention this thing because it will be important in the next time. So when we are using this, when we store this in computer, we don't actually store we don't create a neuron class and we say, okay, this neuron has this many weights and this neuron has these many weights and bias. We don't do it this way. So what we do is we store all of these weights in one matrix. So it's a very trivial exercise, of course, for everyone, but I'll just, so suppose there are 16 inputs here, right? And I want to write all these weights in one matrix such that when I multiply that matrix by this column vector, I should get the output of these neurons before applying activation function. So, I mean, there will be one more step of applying activation, but I just want the weighted sums. So I have this here, okay? So this is x1, x2 till x16, and I have a matrix here. So, and I want the output to be the weighted sum for all the 6 neurons in the hidden layer. Let's call it, okay, I wanted to write Z1, Z2 till Z6. So this is 16 by 1. So what should be the dimension of this matrix? Just anyone just quickly, so I know that you guys are still here. So I want a 6 by 1 here. This should be,
I mean, 6 rows and 16 columns. Right?
and what do you think will be the values in these this row? What should I put in this row with respect to this network?
So the weights that are feeding into Z1, say.
Exactly. So the first neuron. So we have, I hope it works. Yeah, W11, W12 until W1 16. Yeah, W1 16. So this is the weights for the first neuron, and you go on for all neurons, the 6 neurons, and when you multiply that, you'll get this. Now we apply the ReLU over this, or let's say whatever activation function you have, and you get the output of these neurons. And then whatever column vector you'll get after all this, you will again multiply that by this matrix. It would be 3 by 6, and you will get the final output after applying again the activation function. So this is how we store all this. And the final thing is, as I told you initially, that basically this is calculating a function. So let's call this matrix M1, and I also add bias here. So this network is basically doing this thing: F1, F2, F3, F4 of X. So F4 of X will multiply this matrix and add the bias. And then F3, you apply, let's say, the activation function value over Z. Z is a vector. And after that, you again multiply with another matrix, M2, which will represent the weights here. And then you again apply ReLU, and then you'll get the final output. So the net result is composition of all these functions. And so just one simple question, that what if this function, so remember, ReLU is basically like if you have a plane, then it will, and it's going down, then it will just clamp it like this. So it will just make all negative value as 0 and keep all the positive value as they were. And multiplication by matrix can be thought of as like translation, like rotation or something of these like vector space transformations, linear transformation. And adding a basis is just translating it. So it creates a affine subspace that Rn dimension or whichever dimension the Rn after multiplication. So what can you say about this function? So this is what this is a, because everything is continuous here. So the result will also be continuous because composition, and because ReLU is linear function and all of this is linear because multiplication will not convert a plane. So if you're a plane, then it will remain a plane. So this will give you a continuous linear function, a piecewise linear function. And in some dimension, you will find out, okay, so let's just for 3 dimension at least, you will have some planes like this and you will add them. And that is what is going on. So
Yeah.
I will come to this in a bit after when we'll discuss this thing. So I'll try to explain this very quickly, what I meant by this. So now we should go to TensorFlow Playground. Of course, if there's any question, then let me know till now. I hope there is none.
No, I was just going to add, you just said continuous, then you corrected yourself by saying piecewise continuous. Okay, so that should be emphasized.
Yeah, piecewise continuous linear function. Yeah, it's not, it is continuous, but
these are continuous functions, right? But they're not differentiable.
yeah, continuous piecewise linear. Yeah, continuous piecewise linear function. That's why it's continuous piecewise linear. At least when you're applying the ReLU as activation function in that case.
So this is in like these functions are not differentiable everywhere within our domain. So when we do the gradient descent, will that not cause any issues?
No, actually, it won't cause issue because first of all, okay, so what is the cost? So you don't, cost is not fx. So that's why we usually do what we do is we subtract the output, right? So actual output is, let's say, x hat. So I subtract x hat, and then I also take the norm of this, right? And I square that. So this will give you something a bit more smooth. Okay.
I see.
I think it's also that since it's almost everywhere differentiable, it doesn't really matter. If it's 0 is a critical point, then you can just move it to 0.001. It doesn't matter in practice.
I see.
Yeah.
So we'll just.
So I mean, when you apply, yeah. Okay. Go on.
Yeah. So what I'm saying is, we'll just basically while doing the gradient descent, sort of keep choosing the points in a way that the derivative makes sense.
I mean, I think more than that, you have to choose loss functions in a proper way, so that you can. I think for different purposes.
So when you.
Yeah.
Yeah.
No, I think the answer is right. So even if you take ReLU, which is not differentiable at 0, there should be something in the internals where they do make sure that the critical value is not, it's not being differentiated there, which is usually, I think, just moving it a little bit.
Yeah. They do that.
Yeah. Also, in the actual this when you apply this, okay, no, it's not here. So when you apply all this, you start with some point, and it's kind of like when you choose the step size and all, you are approximating everything. So there's we don't actually even need to calculate that precisely. If we are just if we just approximate that, that will also do. So I think maybe they do. I mean, I'm not yet looked into how they do it in the case that when the point is not differential. But I think that by perturbing it a little bit, maybe it will work. Something this should be possible.
Yes.
Okay, so if there is any other question till now. Okay, so let's come to this playground. Okay, so I'll try to explain this in 5 minutes or 2-3 minutes, what is going on here, so that you can play with it. I hope I'm assuming that none of you have seen this, or even if you have, it's just it would be cool to see this. Okay, so the input to this thing is, so this is this is all a neural network, and you can add layers to it, and you can subtract layers, you can add neurons, and you can delete neurons. And the data that you are having is it's basically a binary classification problem, and input will be x1, x2, and every point has a color label to it. So if the input is, let's say 1, 0, 0, then that point has blue color. If there's a point here, I mean, let's assume there's a point here. Similarly, all the points which come here, they all have blue color. And all the points which are here, they all have orange color. So that is what our neural network should learn. So let's just remove this. Let's just make it one single, okay? And even this is single. And let's see if, and even if so these are the inputs. So if I give it just x2, it will definitely not be able to differentiate between these two, because I mean, you need both the coordinate to train it better. So I don't know why even they give an option to this, but still, let's just see what happens when I run it. Okay, so these are the number of epochs that they have. Okay, so you see this line. So this is telling us that all the things below this will be classified as orange. So if I give any input like -6, -6, -6, -5, or any point here in this area, this network will say that it is, okay, I should stop it. This is orange point, and everything above it will be named as blue point. So of course, this is not actually will not classify all these points correctly, because even these points will be labeled as orange. So of course, we should add more neurons. So what is happening here? So what one neuron can do? So by this thickness, you can see the weight. This is -0.86. This is -0.43. So at this neuron, this is the separation that you have between these two areas. And now just think about it, that what is this line? So this is x1, so -0.43 x1, and then you add it to -0.86 x2, and this will give you a if you set it to some, this will give you a plane actually, but if you set this thing to, let's say, 0, so when this value is 0, this whole weighted sum is 0, and that is exactly when you get this line. So the line here, so I don't have a pointer here, so let's just keep your eye here. So this line, it is when this value is 0, and because you're applying ReLU, so everything on one side would be negative and everything on the other side would be positive. All the positive will become 0. And so this is the core idea of this. And now, of course, this one neuron can only create a single line, and this on series, if I even have 2 neurons, they won't do much. Now, if I add one more neuron here, so what do you think? How many planes can it actually now create? So to differentiate between these things, or lines, let's say, not planes. Okay, so anyway, I'll just go with it because there's very little time left. So basically 2 planes, right? So if I run it again, and then we'll see. So there are now 2 planes, and they are both somehow like, it's a much better than previous part. And here, these points are all labeled orange, and all these points will be labeled as blue by this neural network. And we can understand we need at least 3 neurons to make it work properly. If we have 3 neurons, then there will be another plane here, somewhere here, and it will somehow capture all these points and say, okay, all the point inside this will be blue, everything outside will be orange. So let's add one more neuron and let's see what happens. Okay, so this is what we get, and this is much better. Now, if we add one more neuron in this output layer, and this, we'll see this. Okay, this is not actually giving us anything much really better. Let's say 4 neuron. It will approach a circle, almost a circle, as we increase the number of neurons or hidden layers. So if you see this, and actually just increasing, it's not like that you're getting better and better, but still just to see. Okay, so this is what it is doing. So now there are 4 type of data, let's say, labeling that they have. And this is the spiral, and I mean, you should try to figure out what you should select on all these parameters so that it can differentiate these things. So just see this one, if it works or not. Yeah, so it got these quadrants. So this is blue, this is blue, this is orange, this is orange. There are two neurons in output, and it will tell you that if this one is there, then it's positive, and otherwise it's negative. And that's what's going on here. So this learning rate is exactly the step size that we discussed. This is the activation function. So you can try different activation function. What will happen with sigmoid? So you see its learning rate is almost zero. So it's not even learning actually. It's because what they call as vanishing gradient. So because it's so flat that you cannot even learn anything at this point at least. Now use 10H. Let's see if it looks better. Yeah, so I mean, you can see that how fast ReLU actually learns. So when I was using ReLU, and we just do this, and it's in very few epochs actually it learns very quickly. So we'll discuss what this regularization is and or what this technique L1 L2 mean. It's very basic, but still we'll do it next time. So this is batch size. So when we will do the SGD, stochastic gradient descent, we will understand what this batch size means precisely. And so I will just suggest you to go to this site and actually do play with all this. It will give you a good feeling about what's going on. And you can even change the weights by yourself. You can click here and just change it to whatever you want. Okay. So that was it that we have time for today. So if there is any question till now, then let me know. So just for recap, we saw what learning is, we saw what gradient descent is, and we got the intuition for backpropagation, and that is reverse differentiation, reverse mode differentiation. And we saw how to present DNN as matrix. So matrices, not matrix actually. So just one more thing I would like to mention. So you store all the weights as multiples. So there's one matrix for this, one matrix for this. So there are two matrices. If you have 3 layers, then there are 4 layers, then there are 3 matrices, and so on. So this will be helpful when we'll be implementing it on Python. So that's why I wanted to tell you all this, that how you make these matrices, so that when we use Python, so it will be clear that what we are actually doing. And
so can you
next time we will.
Yeah, that's what I wanted. Go ahead.
Yeah. So next in the next lecture, we will see this in detail, and actually there's not much left in this. So we will actually implement it. I will try to implement maybe online, or I wanted to actually give it as an assignment so that you can try it yourself. Even though the code is available online, I won't suggest you to look into that and just actually do it by your own. So it will be nice way to learn all this and get all this concept in your head better. And we'll discuss this underfitting, overfitting, and we'll see a few heuristics that we actually use to build, train and build neural networks. So this is the goal for next lecture. And after that, there will be a tutorial in which we will just summarize everything and finish at least this part. And then we can move on to modeling neural networks via SMT. So if there's any question till now, let me know. Otherwise, we can end.
Any questions? Or any comments you want to add? Sahil, you wrote a long chat. Do you want to summarize what that thing is? What you mentioned in your chat?
I just pasted what I was saying before. I don't think if I've anything to add about the question that Digant was asking. So, and I've pasted in a link in case you want to check out those.
What is that link about? I mean, that has some more information, clarification on that question.
I mean, I think it's pretty straightforward. It's exactly what we were talking about before. So maybe there won't be much value in pursuing the link. I've pasted relevant.
It's about like justification why you use ReLU. Okay, cool. So this link, I think you guys can open that in your browser and actually go through it. I hope it is cool. I don't know. I have not created it yet, but okay. So one thing is that when I actually saw this playground, I was like, just yesterday, I guess, I was confused what all this is. And so I hope that it is clear that what these colors mean and what they are doing. So this is supervised learning, and they are just doing all this cost calculation and everything, backpropagation by it's just doing it by itself. We just have this number of layers and number of neurons at our hand. We can choose all that, and So if there's any doubt about what is going on here, then ask. So because if you don't understand that, you might have to spend like half an hour or something to wrap your head around this. So
Yeah, Hitar, you had mentioned that about a link to some tutorial or some lecture where by someone that
yeah, so yeah, it's about the reverse differentiation, and I will send it to you so you can post it on Moodle.
No, when you say send it to you, yeah, you should post it on Moodle so that people, if they want to, can view that lecture. Is it a video or what? Link to a video?
It's not a video, it's just a write-up. So it's just a write-up.
Okay. I think you should do that. Yeah, so that'll be done. So if you want to read that thing up. So Hitat has based his lecture, is it correct to say that, on that material? Hitat?
The reverse mode differentiation, yeah, I learned from that. I mean, at least I revised it from that thing yesterday. So I think it was good. It's pretty good.
Okay.
So if there's any question about this playground or about this thing, ask, we can end it here.
Yeah, so if there are no more questions, I'll stop.
I just had one quick
go ahead.
Question. Yeah. So if we say have a neural network with exactly 3 neurons in one hidden layer and nothing else, then that neural network should not, like in this particular example, for example, it should not be able to give me more than 3 planes, right?
Yeah.
So
But,
no, I mean, delete the one more layer. There's like 2 layers now. Just make it like one layer with 3 neurons. Yeah.
This one?
Yeah. Yeah. How is this giving me 6 lines instead of 3, Malik? I mean, I don't see where the other lines are coming from.
So
Like,
actually, it will be because I mean it will be because you are applying ReLU over it, right? It's just not the addition of planes. So when you do that, I think because you also have weights, right? So when you multiply that weight and add it, so the result and output that okay, what I will classify it whether as orange or blue. It depends on the number. It's not a binary thing that okay, it's above the plane or below the plane. So it's a number that okay, it's above this threshold. Then you say that it's a
like if there were no
orange.
blue, then it would have been one line only. Or there can be many layers, but there can be many layers and many neurons. But if there were no ReLU, then there would be only one line, right?
Yeah, if I do linear, then it will just you will see this just it's
doesn't
not
matter
giving
the
anything.
number
There's
of
nothing. Yeah, if I use ReLU, then it gives me something interesting. So I mean, I wanted to do that. If you guys have like want to just give me 2 minutes, and I will try to explain. I mean, I have not seen why it's giving exactly these many lines, but it's something related to the thing that I said earlier. That okay, how do I create a new page here? Okay, just 1 second. Okay. Yeah. So it's related to this thing. So let's say we are in 3D, right? And actually this data is in 3D. This playground data is 3D. So for each point you have blue or orange. Let's say we associate some values to that. Blue means 1, orange means 2, or something like that. And the labels has to be converted to number, remember. So you cannot actually input labels as strings. It has to be some number. So let's 1 or 2. We can choose 1 or 2 or something else. And suppose I from one neuron, when I do this, so I'll get a single plane. I mean, I described that very briefly earlier. And this is where it's intersecting the XY plane. This is XY and this is your Z. So now you have, remember the weights are also in picture. So, and now you have another plane, let's say, like this. And there might be multiple, so like different planes like this, but this is intersecting XY plane here. So everything below this is negative, everything above it is positive. Now, if I use linear function as activation function, these planes will add and you will get a new plane, right? It's just a plane. You won't get complex shapes using this. But if you apply ReLU over it, then this part will become 0, and this part will become 0, and then you will get something interesting. So here you will get some, so this is a plane plus plane, so of course you will get a new plane, but at least it's not just a single plane. So there's something like, okay, you're getting some value here. I mean, I don't know what shape it would be, but let's say this is the result. And when you do this with like 3 or 4 planes, I mean, it would be good exercise to understand why this is giving us these many lines and how exactly, because from here you can see the weights and you can see the line for each neuron. So this is for this particular neuron, you have this separation. For this one, you have this separation, and for this one, you have this one. And the result is, of course, pretty different. Of course, these weights play a significant role in that, and there will be some biases. I don't think they are even showing the biases to us here, but so biases might act like shifting the plane. So all the planes are, of course, passing through center, almost to the center. After adding the biases, maybe they will shift, and then you multiply them, and you do the there's a ReLU after shifting. So I think it would be interesting to think about it. You should think about it, how exactly it's giving us 5 lines. So if I figure it out, then I will definitely mention that in the next lecture. But the point is that this is interesting, that if you have a nonlinear function, no matter what it is, no matter how simple it is, even this function max 0x, which is very simple, of course, but still that gives you a lot of power, because just having planes gives you another plane. But as soon as you put this non-linearity in your system, you get really complex geometry that you can cover up using these neural networks. So it would be good if you think about it, and I'll definitely try to give some answer next time. Okay. Any other questions?
So in general, basically, we by giving us the ReLU function, we are sort of splitting a plane into 2 whenever it touches the xy, right? So if you have
Yeah,
2 planes,
exactly.
we're actually combining 4 planes depending on where the xy coordinate is. Like
Yeah,
basically,
but yeah.
yeah. I mean,
So you're saying this plane plus this plane plus this plane plus this plane. So that's why we call it piecewise, continuous piecewise linear. So it's piecewise linear
yeah.
because for every piece you have getting some linearity there, and then you are adding it. So it's the whole thing that you get after doing all this. It will be a linear thing, and there'll be some structure, some shape to it, and but it would be like I don't know what you call it, polyhedron or something. I mean, that shape you can imagine somehow like that.
Got
It's
it.
possible.
Yeah.
Yeah. So yeah, so I mean, definitely think about it. If you come up with an answer, then maybe mention it in the next lecture, and
Can you
try
repeat
to
the
explain that.
question?
Okay.
So what was the basic question? So that why there are
So
3?
he's just asking, yeah, he's asking that when you just have 3 neurons here, so how come the addition is giving you these many lines? So of course it's just something with the addition of planes, but I'm not very sure how exactly these 3 planes are added together with ReLU, so to give us this beautiful partition.
Because it has
So one more thing, when you are okay, so go on. Who was it?
no, go ahead. No. So the planes here was, yeah. Go ahead.
Yeah. So what you can do is, like, you can also change the all thing changes, because when we will discuss stochastic descent, it will help to understand best size shift. So you see, if I increase it too much, it's not actually too good for me. If I decrease it too much, even that's not good. I think my internet connection is stable. Okay, so you should try all that out, and we will like discuss it more in the next one. Okay. Okay, I think we can end it here. So there's
Okay.
I don't think there's any question.